Okay, we could start now. So we have Syed to tell us about Lagrangian flow homology.
Good evening, everyone. Today my topic is the Lagrangian for homology. Lagrangian for homology was introduced by Floer. It used it to tackle the Arnold conjugate. And the Lagrangian for homology is the dimension of the most homology. Then it since the finite dimension be infinite space of infinite dimensions space. And the four function is replaced by the symplectic action function. The going to become the J holomorphic of when the animal is powerful. Now we go to the Lagrangian for homology. Compare symplectic manifold and L0 and L1 be compared Lagrangian submanifold and they must intersect constantly. Suppose future that pi O and Li equal to 0. We also assume L0 and L1 are simple connect. Due to the compactness and intersect conversion, there are finite intersection points of L0 and L1. And pi O and Li equal to 0 mean every topology gives with boundary in Li has 0 symplectic area. Now we can define the space of small pair that being on the small part come from the 0 y cos interval to M and being on L0 and N on L1. And generally we include it in the C infinite topology. Then every constant pair it is corresponding to the intersection point of L0 and L1. We want to define because it is called the symplectically aspherical. We say a symplectic manifold M is symplectically aspherical if the symplectic area of every small pair from the group field to M is 0. When pi L0 equal to 0, M is a symplectic spherical. Since it follows that pi M equal to pi q M equal to pi q M L. Then every spur in M can homomorphic to the Lagrangian submanifold, so the symplectic area must be 0. Then M is symplectical spherical. We define the Gaussian function in the connect component of the part space since the part space is not connect. First, then we consider the universal cover of the part space. This is a pair of a gamma and a cast of the small homocopy. The homocopy is given. Then we define the action function. Now we want to solve the action function are well defined. Then, then we just go homocopy class. Then we can doing it and doing the homocopy and one reverse homocopy to form a cylinder. Now the top on and bottom loop is that and the Lagrangian submanifold. Since they are simply connect, so we can cap them with a topological disk in L0 and L1. This form a group field in M. And on 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 L0 and L1, the form is vanished, so the capping disk has 0 symplectic area. And M is symplectic spherical, so the Coca symplectic area is 0. Then we can solve the action function is well defined. Now we use an almost complex structure. An almost complex structure on a symplectic manifold. It is the engomorphism of an if the square is the negative identity. We say it is omega compatible if it is positive and invariant on the omega for then if uh, omega compatible complex factor that induce a Riemannian matrix on M. Also, the space of compatible almost complex structure is not empty and concatenable. Now, we want to define the tangent space of the universal cover of the component. The tangent space is defined by the vector field and is along cut at the tangent space of gamma I with L0. Now, we choose a smooth family of almost complex structure. We can define a group of Riemann matrices. Then for any good vector field in the tangent space, we define the matrix with the integral of the Riemann matrix. We give the matrix is the integral of the Riemann matrix. So this gives a Riemannian matrix on the space. Now we compute the Eigenvalue. From subset, we can get the Eigenvalue is the dt triangle the partial key. This so the Eigen must be 0 if and only if the partial key is 0, then of the action function if and only if the part is a constant. Similarly, like most logic, we want to define a flow line by the integral the negative Eigen. No. So the negative Eigenvalue equation must satisfy the Cauchy-Riemann equation and the boundary condition. When a map is satisfies Cauchy-Riemann equation, we call it is a J-holomorphic grid. And like most homology, we want to include each J-holomorphic strip, it has connected critical point. So we went into some additional property. We define the energy and that the energy must be finite. So if M is compared, a J homomorphic strip has finite energy if and only if it connects to critical point of the Sn function. Now we define the moduli space of the J homomorphic curve and the J homomorphic and the energy is finite. So, and the mx minus sgn is the script of so by Keyword's theorem, we can say M is decomposite to the MXY. Mhm. If a map is a solution, then any transaction in the X variable is also a solution. This defines an action of the real number the, on the space. Maybe. To remove this deduction, we consider the quotient space MH. We denote MH with the moduli space quotient R. Then we can view the MH as the level set of the action function. Or, sorry. No. To get the degree of index of the critical point, we want to infer some index. So we consider the Lagrangian Grassmannia, the space of Lagrangian subspace in R. Similarly, the unitary group acts considerably on L, and its stabilizer subgroup is orthogonal group. Since the Lagrangian Grassmannia is also to the unitary group quotient orthogonal group. And the determinants map square gives a isomorphism of the four-dimensional group of them. Hence, the four-dimensional group of the Lagrangian Grassmannia is there. For a loop in the Lagrangian Grassmannia, we define the most index of it is the varying number of its image under the determinant square map. Let U is a J-holomorphic U in M. The domain of U is R times 0, 1 cos interval. It is contactable. So the preferred bundle is trivialization. So by choosing a trivialization, the every point of the glue line R times 0 and R prime 1 define a Lagrangian submanifold. So we can consider closed path on the boundary component, and its origin from infinite to negative infinite. This connects the subspace KYL0 to KXL0. And since the groups are conservative, so they must exist an element in the symplectic group such that ATXL0 equal to Rn, ATXL1 equal to IRn. So this gives a path of define a smooth path from TXL0 to TXL1, and lambda x and lambda y, we call it is the canonical subpath. Then by combining the four paths, we give a loop. First, we have the elevation path L0 from TXL0 to TYL0. Next, the canonical path lambda y gives us to TXL1 to TYL0 to TYL1. And the path L1 can go to from TXL1 to TYL1. Finally, the reverse canonical path go back to the TYL0. So, we define the most index of U is this part. And then, more generally, there is an index function such that the index U equal to mu x and mu y. So we define mu x is the most index of the point. So now we introduce the free-form operation. We say a map linear operation is free-form if it has a co-subspace of Y, and if the kernel is finite dimension, and the quotient space is finite dimension. And the free-form index of it is the dimension of kernel F, and the dimension of it co-kernel. In the non-linear case, we say a map is free-form if its differencer is a free-form for all x in X. And we say y in Y is the regular value if every x of the pre-image of Y, the differential map is subjective. Then by the implicit function theorem, the pre-image of Y is a manifold of dimension equal to the free-form index. Now, The moduli space, we can view it as a zero set of the nonlinear Cauchy-Riemann operation on some benefit, and the linearization is a free-form operation. Then PU is the linearization is subjective for generally almost complex structure. Then the modular space is a small manifold of dimension mu x minus mu u. Then, every J-homomorphic connect intersection point x, y if and only if mu x minus mu y larger or equal than 1. If x equal to y, then the moduli space is just x. The index is 0. So now we can define the four complex. The four content complex is defined as a J-group modular generator by the intersection point of the Lagrangian submanifold. And we give the in degree is the most degree of the intersection point. No, sure. We also can define the four differential by counting the sum of points in the moduli space. When we use this is a well-defined, we want to make sure the mxy is finite. Is with some theorem called Gromov compactness. This theorem says every sequence in M has a converse subsequence. By we went to prove it, we went into the elliptic regularity of this. The elliptic regularity, if the gradient is bounded of every n, then un has a converse subsequent converse uniformly on every compact subset of the domain. And the soup of the L infinite gradient defined is the soup of the norm, and the norm is the Riemann matrix on M. This is a position of the this so since the Riemann complex the Cauchy-Riemann, the solution of the Cauchy-Riemann equation are actually most. If un is converse in the W, the Sobel space, so it's also converse to the C infinite local space. We get a start of proof to the elliptic regularity. The elliptic the gradient is bounded if the is continuous and it is bounded since the M is compact. Then we can, by the other of Story theorem, un has a subsequent converse to a continuous map in C. And the subgradient given un is uniformly bounded in the Sobel space by the Poincare inequality. Next, by the elliptic coordinate theorem, un has a subsequent converse only in LP and weakly in WIP. And if un is the solution of the Riemann-Cauchy equation, so we pass to the limit is a weak form solution of the Riemann-Cauchy equation, so it's become a smooth. Then un has a subsequent converse in the previous theorem. Since un equal converse in the Sobel space, so it also converse in the C infinite local space. Okay. We want to prove the gamma compactness. So, by this theorem, we just need to solve its gradient less is uniformly bounded for all compact set as below. We prove it by contradiction. Suppose this Gaussian whole then assume a subsequent UN and a sequence of points S and T and in SP such that the limit of the gradient on the point go to infinite. Then we let epsilon be a sequence of positive number tend to 0. Then the limit epsilon tend to is and the limit of epsilon can be none of the gradient is tend to infinite. When the function of an integrator, we want to include a lemma. This lemma can increment of any location. Since the gradient will go become unbounded larger, a significant concentrate of the gradient magnitude. That's a critical threshold amount. We zoom in the region near the local maxima of the gradient. This lemma so give a way to find the local maxima. By applying this lemma, we get a sequence epsilon and a sequence of points such that subject this. Next, we let Rn be the gradient. We define the QK and is Rm the distance between the point and the boundary of R and the domain. Then it might have two cases observed. Case 1, if the sequence is unbounded, this means the gradient concentrate an interior point. This obtains a sphere bubble. If the sequence is bounded, this means the gradient concentrate at a point on the boundary point. This gives this bubble. In case 1, we define the scalar map and its domain is become larger since the Rn go to larger. And it must satisfy some property. It is the uniformly bounded. So, like the elliptic regular, this implies it has a subsequent converse to V in the C infinite and if the gradient of V0 equal to 1, this so V is a non-constant, and gradient V must less than is bounded. And generally, it must have the finite energy. Since the gradient UN is the solution, it has finite energy. We then go into the removable of singularity. This so that we can scan the map to the sphere and scan the map to a disk. We define the V2K equal to V1 over Z. So it is a smooth. Then by the limit of singularity theorem, it can extend to a smooth map on C. So we can scan to a small cell holomorphic curve, and it is from sphere to M, and its symplectic area is positive, then it is non-constant. Yeah? But this contradiction with the symplectically spherical. Every map or every cell map from sphere to M must vanish. So the bubble cannot occur when M is symmetrical spherical. In case 2, since delta M is bounded, so we assume it can go some delta. Generally, it is 0. And we define, or similarly, we define the scalar map, but its domain is changed. Since every Vn cannot occur the domain of Un, so it is the image on that must lie in the interval. Now, by elliptic regularity, If Vn has a subsequent converse to V and its domain is this by the remove of singularity theorem, we can extend it to this map that is, but it's also contradiction with the pi and L equal to 0. The simplified area of V bar is non-zero. This bubble and this bubble are different. So finally, we improve the Gromov compactness, and then more generally, the sequence of UN, the subsequence is converse to a broken script. Now, so when UX and UY equal to the MH is a finite sense. Since every sequence has subsequent, it cannot, it has not broken set converse to the so they have not, so it has converse to the set in the MX1. Then it is compact, so the quotient space is finite. In the full differential, and this is Gauss equal to 0. When Ux minus Uz equal to 0, the boundary point is the frequency when for all y equal less than u mu x minus 1 and mu z plus 1. Okay. The boundary point of the dimension 1 manifold is even, so the delta square must be 0. Okay. Then this complete this so the four cohomology is well defined. Yeah, and more this the for homology is independent of the juice almost complex structure and invariant under the Hamilton isotropy. Thank you.
Okay, we have 3 minutes left. Qinghao, do you have any question?
Okay, I can say something about there are two things I can mention. The first one is when you like there are three things. One is the symplectic form, the other one is the almost complex structure, the other one is the remaining metric. And then if two of them are compatible, then you can define the third one. But so there's something called compatible triple. In Kähler manifold, like all three work together. But in general, any two can create the other one. And then, but there might be some problem. Like, for example, if you have G and a symplectic form, the J you come up with might not be integrable. So it's still a almost complex structure, not a complex structure. And so that's the first thing. And the second thing I can say is about a J-holomorphic curve. It's basically Cauchy-Riemann equation. That's a function satisfy Cauchy-Riemann equation exactly. And if you remember in complex analysis, uh, holomorphic and Cauchy-Riemann equation, there's still a gap between this and that, right? So you need to satisfy Cauchy-Riemann equation at every point and then a bunch of other conditions in order to be differentiable at each point, right? So J-holomorphic curves are basically function that satisfy Cauchy-Riemann equation at every point, but in general, they are not holomorphic. They're not analytic at all. Yeah. Yeah, so that's two things I can comment on this. Okay. Yeah, that's it.
Okay, thank you. Thank you, Qinghao. So thank you, Sayed.
Thanks the speaker again.